called knot theory. To him, knots are like fingerprints.
We may have something interesting here.
And these knots are a distinct mark of the int virus.
Probably 7.
If he can figure out how the knots are tied, he can see how the virus attacks.
6.
7 or 9 crossing line.
1, 2,
Focus it a
3,
little bit.
4,
So that's
5,
a nice
6,
knot. It just
7,
happens to
8.
have another
I'd probably
molecule.
could say 9.
You know the kind of DNA you're inserting into these experiments. The enzyme takes it in the back room, does something to it, and out the door comes an interesting topological form, like a knot or a spectrum of knots. And then the problem is to figure out what happened back there where you can't see it.
The first step in the process is to identify the knots.
Over, under.
Knot theorists have been identifying knots for more than 100 years. And over that time, they have classified more than 12,000. One way they distinguish knots is by counting crossover points. For example, this knot crosses itself 6 times. Another way to identify knots is by manipulating them. Knots can be rotated, twisted, and stretched. Until recently, knot theory hasn't had any application in the real world. Today, however, knots are popping out of the textbooks and turning up in some interesting places.
That's a good guy.
The excitement about seeing knotted DNA is that you're recognizing old friends, these knots, the ones you've seen in textbooks. Here they are turning up in real life. They've become in the flesh. So this is terrific.
One of the knots the int virus has tied crosses itself 3 times. Sumners wants to figure out how this knot was created. In his work, Sumners relies on drawings, rubber tubes, and photographs as he tries to untangle the viral knot. He knows that the DNA starts out coiled. He's beginning to see how the enzyme bends the coil, bringing 2 points close together. Next, the enzyme cuts the DNA, and it forces the 2 strands to change position. It's at this critical point that the virus is inserted. If they can stop this step, they can stop the virus. Enzyme by enzyme, knot by knot, Sumners and Spangler are beginning to see how viruses work. Ironically, knot theory, which was never meant to be applied to real life, may someday help stop disease.
It's a constant battle to fight with viruses, and any tools we can have in this battle are good ones. So it's know thy enemy in that sense. Anything and everything you know about them can and will be used against them.
You can get any requirement. And clearly when you have...
For hundreds of years, mathematics and biology have been separate disciplines. To Spangler and Sumners, the future looks quite different.
Lots more dinners, lots more walks, lots more talking.
Lots more talking.
Lots more playing with ideas.
That's mathematicians and biologists.
One of mathematics' greatest powers is its ability to describe things. Circles, triangles, rectangles. These geometric shapes can be used to describe things we make with remarkable precision. But when it comes to Mother Nature, she seems to be coloring outside the lines. What shape is a flower? What are its characteristics?
When I am looking at plants, what I find beautiful is their shape and form. But there is also another layer of beauty. We could say that it is a little bit hidden beauty. It is not what we see at first sight when we look at a plant. It is the beauty of the understanding of the mechanisms which bring this form about.
Przemysław Przemyskiewicz, or Dr. P for short, studies plant growth. And in his work, he turns to a new geometry that begins to describe nature's forms. This new geometry is based on something called fractals. Fractals are unusual shapes that mathematicians began creating at the turn of the century. They are unruly and intricate, and they are different than traditional geometry. To create a classical fractal, take a triangle and add a triangle to each side. Repeat the rule forever, and the Koch snowflake is formed. In the 1960s, mathematician Benoit Mandelbrot pointed out that these old forms have several striking characteristics. First, very intricate shapes can be created by repeating simple rules. And second, small parts of the shape look like big parts. Mandelbrot named forms like these fractals, and he created a famous fractal of his own.